and I'm going to show you today how the pressure chamber works. We've got pressurized air in this cylinder that's then regulated, goes through that pipe into this cylinder, and we can regulate how much is going into the cylinder from here, and got the gauge. Then we've got the leaf or roots or a whole shoot in this cylinder sticking out through the lid. Pressurize that, and what we want to see is the first droplet of water coming out of it. So what you need is obviously the pressure chamber, a pair of goggles, really important because we're working with high pressures, and if something goes wrong and things blow up, you don't want to have anything in your eyes. You need to look very closely, so for some people it's easier to use a magnifying glass as well. If you want to collect xylem sap, you need a pipette and tips for it, and to prepare the lid you need a selection of grommets. When you are sampling your leaves or roots, always remember you're working with a living organism and they are responding to their environment. So always make sure that you sample in the environment that they were grown in. Do not take the plant and walk over to the lab and sample there, because while you're walking there, you're in the corridors, light intensities are not as high, even in the lab and bright lights. Stomata will close, the leaf stops transpiring, and then more water comes into the leaf, and you will not find the differences that you would have found if you stay in the greenhouse with them. For sampling a leaf, make sure you've got a sharp blade, because we need a very clean cut. That will make it much easier later on to see when the sap comes out of the stem. Take the cut in a 90-degree angle to the stem of the leaf. Doesn't necessarily have to be in line with this stem. Make sure you've got some space for the leaf to go through the head of the pressure chamber. So cut it relatively close to the stem. In one go, get through it. And there you go. The leaf goes into a plastic bag and blow into it. Blowing into it is important because the leaf keeps transpiring, and we want it to lose as little water as possible on the way into the lab. So now we want to be quick. Okay, sample out of the bag. Carefully get it into that hole. Try not to damage the stem. And now you screw the top and thereby squeeze the grommet so that it fits tightly around the stem. It is important that it's tight enough so that no air escapes from between the stem and the grommet, but not so tight that you squeeze the stem so tight that the vessels get damaged. Because then obviously there's no water coming through. And now insert it into the chamber. The red button turned makes it sure that there's pressure actually possible to go in, and with the valve you can adjust how much pressure is going in. So while I am increasing the pressure, I'm looking at the stem surface very closely. I do not look at it from the top, because if it fails and the whole thing shoots out, things will land in my face and might injure me. I also don't want the lamp to be right on top of it, because it might get broken if something shoots out. Because again, we're working with high pressures here. I always have my hand on the valve, because if something starts to move, if I hear air escaping, I can immediately shut down the supply of more pressure and then release the pressure with this valve. Now that the leaf is inside the chamber, dab the top dry, because there's always a little bit of sap from the cutting on top of it. and then you slowly increase the pressure. If you hear air escaping, screw it a little bit tighter, stop the increase of the pressure immediately. If you see it moving, stop the increase of the pressure, release the pressure a bit, and I hope you can see that's where the first water comes out. So we can read from out here, this is bar, that's 5.4 bars or 0.54 megapascals. Right, and once you've finished your reading, if you don't want to take Xylem sap, all you need to do is make sure this is closed, decompress the chamber, so release the pressure, and then you can unscrew the tap. And see, the leaf is still absolutely intact. And also the stem still looks absolutely fine. So we haven't squashed vessels, so we can be sure that the readings we have actually make sense. So what happens with the leaf inside the pressure chamber is the following. We have air compressing it from all sides at growing pressure, and you can imagine that like a sponge. And if I have a very wet sponge, so there's a lot of water in the leaf, I only need like very small pressure to get some water out. But if the sponge is a little bit drier, I have to squeeze like much stronger to actually get the water out there. So this is what we're doing in the pressure chamber with the leaf. We're squeezing the leaf until the first bit of water comes out, and the pressure that we need to squeeze the water out is equivalent to the negative pressure with which the leaf is holding the water inside. And it's actually also equivalent to the pressure with which the leaf is pulling water through the whole system into the leaf. When you're sampling for root water potential, you need to cut obviously as low as possible to the roots, because you don't really want to measure the stem, but you always need to make sure that you can still fit it through the head of the chamber. So I would need to cut it like roughly here. Again, we want to have a clean cut as straight as possible to make the measurement easy later on. If we still have leaves on the sides, for the measurement, we would need to cut these as well and wrap the whole stem with parafilm so that the sap doesn't come out of these wounds, but actually only comes out at the top. For measuring root water potential, we now brought in our pot that fits exactly into the cylinder and cut the shoot in the greenhouse. Now we want to be quick, fit the shoot in there, and now we first fit the lid and then fit the metal rings and the grommet around the bit of the stem that's sticking out. The principle for the stem is the same. We increase the pressure slowly until we see the first bubbles coming out. And this is 1.2 bars. So now that we've taken measurements, I want to bring this a bit more into perspective for you. So we've got water in the soil, well-watered plants, that is taken up by the roots, and the roots obviously hold a bit of the water, and then the leaves need to get hold of the water, so they suck water through and transpire it again. And through that transpiration, there's a lack of water in the leaf that creates a stronger negative pressure, so a lower value, that makes sure that more water is transported from the root up to the leaf. And actually that's what we've seen. We've seen a value of minus 0.12 bar in this case, for for the root and a value of -5 or 6 bar for the leaf. That's a huge difference. And just to give you an idea what kind of suction power that is, when you drink a cocktail with a 30-centimeter long straw, you suck the drink through the straw with a suction power of 0.03 bar. Don't quote me on this, all this is like Wikipedia knowledge. I just wanted to get some data so you get an idea of the order of magnitude that we're talking about here. So 0.03 bar when you suck on a straw. A vacuum cleaner has a suction power of about 0.2 bar. That's 10 times more than you drinking a cocktail, okay? But the plant, like the leaf, has a suction power of like 5 or 6 bar, and that's a well-watered plant. That is 20 times more than a vacuum cleaner. Just to get you an idea, I mean there are better and worse vacuum cleaners obviously, but just to give you an idea how much pressure is going through this tiny plant, I think that's amazing. And why does it need such a high pressure? Well, there's a couple of factors. Obviously, the leaf loses a lot of water through transpiration. If the plant wants to do photosynthesis, it needs to open the stomata, and through opening the stomata, it will necessarily lose water vapor. So there is water lost, so it needs to kind of transport it back. But it does not only transport it back through a flat surface, this has to go against gravity. So the leaf needs to work against gravity. Then the root itself, the cells in the root, will hold some of the water, so it needs to work against the root water potential and the water potential of the soil as well. As the soil dries out, it will get harder for the plant to suck the water out of the soil as well. And then you've got these tiny little vessels, and there's obviously the friction of the sap going through the vessel all the way up. And the plant, the leaf, has to work against that friction as well. So it makes sense that the soil water potential is closest to 0. Then the root water potential is a little bit more negative because the root needs to suck water out of the soil. And then the leaf water potential is the lowest of all because it needs to make sure that all water goes through the stem and into the leaf so that the chemical processes actually can happen. So I hope this video did not only tell you how the pressure chamber works, but spark some interest in this kind of measurements and tell you a bit more like why plants are amazing and why plant-water relations are something that are well worth studying.